Hey everybody, in this video we're going to be practicing Rolle's theorem. Now some of you may not be familiar with Rolle's theorem because some textbooks don't cover it. Rolle's theorem is a specific application of mean value theorem where we pick an interval of a function and we want the endpoints of that interval to have the same value, so that when we draw the secant line the slope is always 0. Now with normal mean value theorem you can pick any 2 points of a differentiable function, but here for this application all the endpoints are the same y value, and therefore the secant line is going to have a slope of 0. And so therefore we're looking for the tangent line that has a slope of 0. So that's what's called mean value theorem. If you want to follow along, the links to the companion worksheet are in the description below. So let's get started. So for this first three, we just want to look at why Rolle's theorem does not apply for the function on the interval that they've given us. And so the first thing to check is, well, do the endpoints have the same value? That's a first good place to start. So we go from -5 to 1. So if we plug in -5 for x, what would we get back for y? Well, if we plug in -5, add 2, we get -3. And since we have the absolute value, that makes it +3. And we do the same thing for 1. If we plug in 1, add 2, we get 3, and the absolute value keeps it positive. So the endpoints do have the same value. So that's not the issue. What is the issue is the shape of the graph. And so when we have absolute value, here we've got absolute value. And what the +2 is, it shifts the normal absolute value graph 2 places to the right. And so here's what the absolute value function here is looking like. And right here, right at the vertex, it's not differentiable. And that's the problem. It needs to be differentiable on this entire interval in order for Rolle's theorem to apply. So even if you have just one spot that's not differentiable, we throw it away. We discard it. So that's the reason why number 1, the Rolle's theorem doesn't apply. So let's look at number 2. Here we've got this function on the interval of 4, 6. So if we plug in the endpoint 4 in for x, 4 minus 3 is 1, square root of 1 is 1. And then we have 6. Plug in 6 minus 3, square root of 3. Well, that's a problem, because those two are not the same. And because they're not equal, Rolle's theorem doesn't apply. So that's the problem with these. So looking down at number 3, here we've got t squared over t minus squared minus 1. So if we plug in -2, we get 4 on top over 4 minus 1. So that's 4/3. And then on the bottom we plug in 2, so that's 4 over 4 minus 1, which is also 4/3. So that's not the problem. But what is the problem is that because we have a denominator with an variable expression, we could have this equaling 0, and that's a problem. And so when does the denominator equal 0? If we solve for that, we get t squared equals 1, so t equals plus or minus 1. And at these values, f of x is undefined. And the problem with that is that if it's undefined, then it can't be continuous. And if it's not continuous, it can't be differentiable. So at these points, f of x is not differentiable, and it needs to be differentiable at every point. So that's the reason why this one fails Rolle's theorem. All right, looking on to the next one. So here, for this one, Rolle's theorem does apply. And if you want to check it yourself, you can, in that if you plug in 5/2 and 3, you get the same y values for those endpoints. So what we're going to do is we're going to ask where on this interval is the slope equal to 0. So we find f prime. So f prime is going to equal 4x minus 11. And we set that equal to 0. And now all we have to do is algebraically solve this. So we add the 11 over. So that's 11 equals 4x, and x equals 11/4, which as a decimal equals 3.75. No, I'm sorry, that is 2.75. And so 2.75 is indeed on this interval. So that is the x value that we're looking for. Oftentimes they use a value of c, but it works the same way. So now, moving on to number 5. Here our endpoints are -5 and -1. So we find our derivative. G prime of a equals 3a squared plus 10a minus 1. And so we set that equal to 0. So 0 equals 3a squared plus 10a minus 1. And unfortunately, this one is not going to factor at all. So because it can't factor, what we'll do is we'll reach for the quadratic formula. So -b, so that's -10, plus or minus the square root of b squared, that's 100, minus 4 times a, which is 3, times c, which is -1, all over 2a. So that's 2 times 3. So what we can do is we can take -10 plus or minus the square root of 112 all over 6. And so a little practice with factoring 112 to see how can we simplify this radical. Well, I can take a 2 out of 112, and that leaves me with 56. I can take another 2 out. That leaves me with 28. Another 2 leaves me with 14. Another 2 leaves me with 7. So 112 is the same as 16 times 7. Now the 7 obviously is a prime number. We can't take the square root of that. But 16 we can take the square root of. So a equals -10 plus or minus 4 square root of 7 all over 6. And we can simplify by taking a 2 out of everything. So -5 plus or minus 2 square root of 7 all over 3. And those are the exact values. Now one thing to be aware of is you have to check to see, do both of these values fit into this interval? Because it is possible that one value may be in the interval and the other not. So if I take -5 plus 2 radical 7 over 3, I get approximately 0.097. And I also get negative, if I subtract, -3.43. Now, Rolle's theorem and mean value theorem also only concern ourselves with the values that are within the interval. So actually, we don't count that. We don't count the values outside of the interval in question. We only focus on the values within the interval. So -3.43 would be the only answer, or -5 minus 2 radical 7 over 3 if you're writing it exactly. So let's go on to the next one. Now here we've got the interval from 0 to 6. And so when we take our derivative, we have p prime of t equals 16 thirds. T to the 1/3 minus 8 t to the -2 thirds. And so because it's Rolle's theorem, we're going to be setting this equal to 0. So 16 thirds t to the 1/3 minus 8 t to the -2 thirds. Now at this point, what I'm going to do is I'm going to write everything back in radicals. Now in calculus, we tend not to do that. We tend to prefer exponents. But we've already done the derivative part up here. And so everything at this point is just going to be algebra. And algebra prefers radicals. So I'm going to write this as 16 thirds times the cube root of t minus 8 over the cube root of t squared. So first thing that I'll do is I will rationalize that denominator. So we'll multiply cube root of t all over cube root of t. So 0 equals 16 cube root of t over 3 minus 8 cube root of t over t. And now we're subtracting fractions, so we will need a common denominator. So I'll multiply this fraction top and bottom by 3, multiply this fraction top and bottom by t. So what we get is 16t times the cube root of t all over 3t minus 24 cube root of t all over 3t. So now that we have the same denominator, now we can write them as a single fraction. So we have 16t cube root of t minus 24 times the cube root of t all over 3t. Now what we want to know is what values make the fraction 0. Well, if the bottom were 0, that would be undefined. So what we do is we just make a note off to the side that t cannot equal 0. And so all we do now is we just focus on what values will make the numerator 0. Because if the numerator is 0, as long as the denominator is not 0, we're okay. So we have 0 equals 16t cube root of t minus 24 cube root of t. So we factor out an 8, and we factor out a cube root of t. And we're left with 2t minus 3. So now we can set those two parts equal to 0. 0 equals 8 cube root of t, and 0 equals 2t minus 3. So here, I'm going to divide by 8. So 0 equals cube root of t, and then I raise both sides to the third power. So 0 equals t. But wait a minute, that violates our assumption up here. So actually we have to say that, oops, that's not a solution. It's undefined. But over here, I don't think this will be 0. If we add 3 to both sides and then divide by 2, we get 3 halves. And 3 halves is in the interval. So this is the value on this interval where the slope is 0. All right. So on to this last one. We want to find this derivative. So j prime of x is going to equal, we're going to need quotient rule. So low, so x squared plus 4, d high, which is 2x, minus high, x squared minus 4, d low, it's 2x, all over low, low. So x squared plus 4, quantity squared. And we'll simplify this. So we get, we'll expand this out, 2x cubed plus 8x minus 2x cubed plus 8x all over, and we'll leave the denominator in factored form. No point in expanding that out. So the 2x cubes cancel, and the 8x's combine to get 16x all over x squared plus 4 quantity squared. And again, we're setting this equal to 0. Now, the nice thing about this example is that the denominator will never be 0. It'll never be undefined. Why? Because the smallest that x squared can be is 0, and that's if we plugged in 0. But then we're adding 4 onto that. So 4 is the lowest that this could be, and then we're squaring it. So 16 is the lowest that this denominator could ever possibly be. It can't ever be 0. So we don't have to worry about any values making it undefined. So what values will make it equal to 0? Well, we just look at the numerator, divide by 16, and we get 0 equal to x, which is in our interval. So that's the number we're looking for. Thanks so much for watching. If you liked the video, please give a thumbs up. For more videos like this, click the subscribe button. If you're a teacher and you like this, please share it with your colleagues or students. If you're a student and you liked it, please share with your classmates. If you have suggestions or problems you want to see worked out, type a comment below. To support the channel, click the Patreon link to help keep this going. Thanks so much for watching, and remember, the best way to understand something is to do it.